So hello everyone, my name is Prachi and today I'm going to present my project on image classification in edge computing using Orchestra framework with deployment on Raspberry Pi devices. As edge computing has emerged to address the challenges of latency and data privacy in real-time application like smart surveillance and smart surveillance, industrial IoT, autonomous navigation, AR, VR experiences. These application requires that data be processed close to where it's generated, and that is at the edge. But the main issue with the popular orchestration system like Kubernetes are built for cloud environment. They assume they have a high availability and high bandwidth, reliable and low latency network, which is not true for the edge devices. So edge devices like Raspberry Pi are having some constant in CPU, memory, and network connectivity. So we need a new orchestration framework that is light, dynamic, and robust. That is where the orchestra comes in. So the main motivation behind orchestra to build a system, that can run on resource-limited hardware and support multi-providers and enables fault-tolerant and dynamic service management. And it is fully open source and designed for real world scalability and flexibility. The orchestration layer and the minimizing the dependency, Orchestra creates more adaptive and cost efficient environment for deploying microservices at the edge. So the Orchestra architecture consists of three-tier hierarchy. In that hierarchy, first comes root orchestrator, which makes global scheduling decisions based on the most suitable cluster for service. Next is cluster orchestrator, manages nodes inside a cluster and makes a final grind decision. And next comes as devices like Raspberry Pi that's actually run the services like image classifier. So in orchestrator, basically it's a component responsible for deciding where the user services should be deployed based on the SLA, service level agreement, and current resource availability across the cluster. So basically the job life cycle of the root orchestrator consists of request, scheduled, and running and failed. So first is requested, the user submit a request to deploy a service. Next comes is scheduled, where the root scheduler select the most appropriate cluster to run the services. Next is the service is successfully deployed and the operational, it's a running state. And next is our fail, if the deployment failed due to the resource mismatch and the network error or SLA violation, so we can send our services to the next cluster. So the design component in our root scheduler, basically it consists of four states. First is REST API Flask. The root scheduler exposes a Flask based REST API endpoint, and the system manager sends HTTP request with job details, example like SLA and microservice definition. And next come is salary task queue, a synchronous task manager to process jobs in the background. And basically it enables scalable and handling of multiple deployment requests. Each job is processed individually and non-blockingly. Third come is Redis backend. Redis is used as a message broker for salary, and jobs are pushed onto Redis queue by the Flask APIs, and the salary workers continuously polls Redis to fetch new jobs. And next come is salary worker. The worker picks up jobs one by one and process them. It matches the SLA with, if it's matched with the SLA, then it will going to assign the worker to that. It will assign the cluster, and after that computation after the computation it sends the decision back to the system manager. So basically here we define the job, each job with a set of CPU, RAM, latency, and location. And we are going to find the best cluster fit with the help of this optimization function. And next come is our cluster scheduler. Here basically a cluster scheduler is a component that decide basically which worker should get the Basically, it decide which worker node should run a service after the root scheduler has already chosen the cluster. The internal flow for this cluster scheduler is, first it will receive a job. A job J is received basically with the help of Flask and REST endpoint. Next is queuing with the help of Celery and Redis. Celery adds J jobs to a Redis queue. A Celery worker fetches and processes it. Next is filter eligible nodes. If a node is eligible, it will be there will be a eligibility criteria for each worker node with the with is it if it have enough CPU and RAM, and if worker node is active. Next is how we are going to prioritize the nodes for each worker. It should be compute with a score with the multiplication of the weights. Next we are going to find the best fit worker with the help of this optimization score and each level basically only handles the complexity appropriate to its scope and communication. So the communication is also optimized with the help of MQTT for light intra-cluster communication and REST API for inter-cluster messages. This modularity ensures orchestra can scale for 10 to thousands of edge devices. And this approach of scheduling ensures the load balancing and resource optimization and low latency deployment. So next is the implementation detail. This is the brief tech stack for the orchestra. Here we have um, defined the files for the orchestra, and the MongoDB basically is basically for storing the SLA and all the containers information, and MQTT basically a communication protocol for intra cluster messaging, and this stack is optimized for performance and portability and low overhead, essential for Raspberry Pi deployment. So next is our workflow for image processing. So first is uh, an worker node, which is a Raspberry Pi captures an image from its camera. A deployment request with SLA is sent to the root scheduler. Next, select a cluster, and that cluster scheduler select the best Pi node, and Pi uh, the node engine on that worker node download the image classification container example using TF Lite model. The image is processed locally, and the result, such as the image is detected, is either sent to a central dashboard and is it or shown on the Raspberry worker node itself. So basically, this is how we are going to assign our worker node to the cluster orchestration with the help of some bash commands, and this will show our this will show our node engine status that it is connected to the cluster orchestration. And next is so the system basically supports continuous streaming where the services stays live and multiple frames can be processed in a real time, and the networking and the fault tolerance basically handled with the net manager. So the orchestra net manager handles advanced networking needs. It basically provides semantic IP routing and proxy to tunnels for secure cross cluster communication. For fault tolerance, if the worker nodes like a Pi for a worker nodes like a Raspberry Pi model fails, the cluster redeploy the job to another node. If an entire cluster goes offline, the root will assign services elsewhere. This is done automatically with the cast state and retry policy. It also support eventual failures strategies for orchestrator through a multi-masters is planned future enhancement. And next come is our monitoring and results. So here we can see that the CPU usage is a less than 30%, and latency is 52 millisecond, which is very good. And this kind of monitoring is essential to optimize the performance and identify and improve the quality of services. So the network performance up to 35% better than the round trip times under load. These improvements are not marginal, they are critical in edge environment where every millisecond and milliwatt matters. So the conclusions are like Orchestra is a lightweight hierarchical fault tolerance orchestration framework, and it enables the real-time image processing on the devices like Raspberry Pi, making it ideal for intelligent edge applications. And its modular design allows for extensibility and real-world deployment scale. So yeah, so you can so the project is open source, and you can read the full paper from this site. And thank you so much.